In this next segment of the video, we're going to be taking a look at expressing the idea of conservation of energy mathematically. Now, the conservation of energy, all that says is that energy, the amount of energy you start with, ought to be equal to the amount of energy that you end with. We'll be focusing on three ways that energy is stored specifically. PE, KE, and EE, that is energy stored positionally, kinetically, and elastically. And those three together are known as mechanically stored energy. All right, and so if we want to express the idea that, well, you have some energy to start with, and then you might have some energy that leaves the object you're interested in, energy that comes in, and then you have some final energy. So to express that, we can say the energy initially stored mechanically plus any energy transferred into or out of mechanical storage should equal the final amount of energy stored mechanically. Now, the reason we're focused on mechanically stored energy, these three, is because those are the three that are most applicable to the systems that we're going to be looking at. Now, we can write this symbolically to say that mechanically stored energy initial plus work done, this energy transferred in or out of mechanical storage, that's what's meant by work. Work is energy transferred. So energy you start with plus energy that comes in or goes out is the energy you end with. That makes sense. It's kind of like a checkbook or a bank account. Now, how would you know if work was done, if energy was transferred into or out of the object or system? Well, typically it will happen if you have some energy that's stored chemically that's somehow transferred to KE or PE. For example, that's what happens when you start to run. The energy that's stored in your body gets transferred to, chemically gets transferred to kinetic storage when you start to move. It also happens if you have KE, PE, EE, which is transferred to thermal. So for example, sliding across a tabletop, a book will start with its energy stored kinetically but end with its energy stored thermally. That's another clue that work has been done. Now, over the course of the next couple questions, we'll see how these ideas apply. All right, so let's take a look at this question. So we've got the cow back up on the hill. Here's our hill right here. Here's our cow, and that's 10 meters high. I want us to draw an arbitrary but usually common sense level of where we're going to measure our height from. And then let's denote this point A and this point B, Y point A and point B. We want to know how fast she's going to be going at the bottom of the hill, so B, which is at the end of the cow's trip down the hill. And what we're going to use is the idea of mechanically stored energy. So let's do a couple of pie charts to represent this. So up at the top of the hill, the cow stores energy positionally. And if you want to pause it and tell me how the energy is stored at the bottom of the hill, you do that, and then I'll be right back. Well, at the bottom of the hill, it's moving, and it's no longer above this height equals 0, so all of the cow's energy is stored kinetically. Those pies give us a clue as to how to write out our equation. In the beginning, we can look at this pie and see that the only form of mechanically stored energy is PE. So PE at point A, there's no work done because there's no friction and there's no chemical energy involved. And then at the end, so plus 0, and then at the end, at point B, at the final, the energy is all stored kinetically. And that's at point B. Now, this is mgh, which we can calculate, and this is 1/2 mv squared. Now let's put the numbers in. 500 times 9.8, this is the same cow as we had before, times 10 equals 1/2 times 500 times v squared. You can pause the video and calculate that for yourself. Did you get 14 meters per second? That's how fast the cow is going at the bottom of the hill. And we used our idea of conservation of energy to determine that. In the next segment, look at another example.